Welcome student in the lecture series of heat transfer. It's chapter number 2, conduction heat transfer, part number 3. In this lecture, we will discuss about two topics, critical thickness of insulation and examples. Also discuss about heat transfer through extended surfaces, fins. So let's start our lecture. First, let's discuss about the general aspect of insulation. A material which retards the flow of heat with reasonable effectiveness is known as insulation. It is used for the following two purposes. It prevents the heat flow from the system to surrounding, and it prevents the heat flow from surrounding to the system. Adverse to the common belief that addition of insulating material on a surface always brings about a decrease in the heat transfer rate. There are so many examples when the addition of insulation to the outside surfaces of the cylinders or sphere does not reduce the heat loss. These are the field of application of the insulation like boilers and steam pipes, air conditioning systems, food preserving stores and refrigerators, insulating bricks, prevention of liquid gases, and insulation of underground cables. Asbestos, plaster of Paris, porcelain glass, wood, glass wool, mineral wool, thermocol are some of the example of insulating material. Also, some of the important factors which affect the thermal conductivity of the insulators. The value of thermal conductivity should be always low to reduce the rate of heat flow. So number 1, the temperature. For the most of insulating material, the value of thermal conductivity increases with increases in temperature. The second one is density. There is no mathematical relationship between thermal conductivity and density. The common understanding that high density insulating material will have higher value of thermal conductivity is not always true. Third one is the direction of heat flow. For most of the insulating materials, except few like wood, the effect of direction of heat flow on the values of thermal conductivity is negligible. Fourth one, moisture. It is always considered necessary to prevent entrance of moisture in the insulating materials during service. It is however difficult to find the effect of moisture on the value of thermal conductivity of different insulating materials. Fifth one is air pressure. It has been found that the value of thermal conductivity decreases with decreases in pressure. And sixth one, the convection in insulators. The value of thermal conductivity increases due to the phenomena of convection in insulators. As I said, under certain circumstances, it actually increases the heat flow upon certain thickness of insulation. The thickness up to which the heat flow increases and after which heat flow decreases is termed as critical thickness. Let's derive the formula for critical thickness of insulation for cylinder. Here consider a solid cylinder having a radius R1 and insulation thickness of R2 minus R1. L is the length of cylinder, which is not shown in figure. HO, or say the H0, is convective heat transfer coefficient at outer surface of insulation. K, the thermal conductivity of insulating material. T1, the surface temperature of the cylinder, and T air, it's a outside temperature of air. So the rate of heat transfer through cylinder with insulation is given as from the Fourier's equation delta T divided by RTH total. So Q is equal to delta T divided by RTH total. So delta T, that is the temperature difference between the surface temperature T1 minus T air divided by RTH total. So thermal resistance of the cylinder, that is inside the bracket Ln, R2 by R1 divided by 2 pi KL plus 1 upon HO into 2 pi R2 into L. That 2 pi R2 into L, that is the surface area of the cylinder. Take 2 pi L here common. So we get Q is equal to 2 pi L into bracket T1 minus TR divided by inside the bracket ln R2 by R1 upon K plus 1 upon HO into R2. So now from this equation we can say that if R2 increases, the factor ln R2 by R1 divided by K increases, but 1 upon HO R2 decreases. So Q becomes maximum when denominator becomes minimum. So differentiate the denominator with respect to R2, that is outer radius, and equate it with 0. So dR2 inside the bracket ln R2 by R1 divided by K plus 1 upon HO into R2 is equal to 0. So let's simplify it. D dR2 inside the bracket ln R2 by K minus ln R1 by K plus 1 upon HO by HO into R2, that is equal to 0. So derivate the first term ln R2 by 1 upon R2 plus that term is equal to 0 plus 1 upon HO inside the bracket, the derivation of 1 upon R2, that we know that minus 1 upon R2 square and is equal to 0. By the further simplification we get 1 by K minus 1 upon HO R2, that is equal to 0. Here take 1 upon R2 negative and so we get this term. Finally the R2, that is equal to critical radius, is equal to K by H0 we get, that is the most important equation. That relation represents the condition for minimum resistance and consequently maximum heat flow rate. The insulation radius at which the resistance to heat flow is minimum is known as critical radius. The critical radius is dependent on the thermal quantities like thermal conductivity and convective heat transfer coefficient HO, and is independent of R1, that is the cylinder radius. It may be noted that if the second derivative of the denominator is evaluated, it will come out to be positive. This would verify that the heat flow rate will be maximum when R2 is equal to RC, critical radius of the cylinder. In physical sense, we may arrive at the following conclusions. Number 1. For the cylinder bodies with R1 greater than RC, figure number A, the heat transfer increases by adding insulation till R2 is equal to RC as shown in figure. If insulation thickness is further increased, the rate of heat loss will decreases from this peak value. But until a certain amount of insulation denoted by R2 dash at B is added, the heat loss rate is still greater for the solid cylinder. This happens when R1 is small and RC is large. The thermal conductivity of the insulation K is high, poor insulating material, and HO is low. A practical application would be the insulation of electric cables, which should be a good insulator for current but poor for heat. While in second case, for the cylinder bodies with R1 is greater than RC, the heat transfer decreases by adding insulation as shown in figure in B. This happens when R1 is large and RC is small. A good insulating material is used with low thermal conductivity and high convective heat transfer coefficient. In steam and refrigeration pipes, heat insulation is the main objective. For insulation to be properly effective in restricting heat transmission, the outer radius must be greater than or equal to the critical radius. Now let's derive the critical thickness of insulation for this sphere. Consider a solid sphere having a R1 radius insulated with the insulation thickness, that is R2 minus R1. The equation of heat flow through a sphere with insulation is given as from the Fourier's equation Q is equal to delta T upon RTH total. RTH, that is thermal resistance. So that Q is equal to delta T, that is T1 minus T air, that is T1 is the surface temperature of sphere and T air, that is outside temperature of the air. So divided by the divided by the thermal resistance. So here inside the bracket R2 minus R1 divided by 4 pi K R1 into R2 plus 1 divided by 4 pi R square into HO. HO, the heat transfer coefficient at outer surface of insulation, and the K is the thermal conductivity of insulating material. So adopting the same procedure as that of the cylinder, ddR2 inside the bracket R2 minus R1 divided by 4 pi K R1 into R2 plus 1 upon 4 pi R2 square into HO, that is equal to 0. Take 4 pi common and we cancel out. So ddR2 inside the bracket R2 minus R1 divided by K R1 into R2 plus 1 upon R2 square into HO is equal to 0. So by further simplification we get 1 upon 4 pi ddR2 inside the bracket R2 divided by K into R1 R2 minus R1 divided by K into R1 R2 plus R2 square into HO. Here R1 R1 cancel out, R2 R2 cancel out. So remaining equation is ddR2 inside the bracket 1 upon KR1 minus 1 upon KR2 plus 1 upon R2 square into HO. So now derivate this equation. So we get the derivation of 1 upon KR1, that is equal to 0, and remaining is 1 upon KR2, the derivation is 1 upon KR2 square minus 1 upon R2 square into HO, the derivation is minus 2 divided by R2 raised to 3 into HO, that is equal to 0. So we get R2 cube into HO, that is equal to 2K into R2 square. Finally we get the equation of R2, that is equal to RC, the critical radius of insulation for the sphere is equal to 2K divided by HO. In exam, so many times the derivation asked by the university, so it's very important derivative for the university exam. Let's learn the example based on these two derivatives. That is the given data. A 10 mm cable is to be laid in atmosphere of 20 degrees centigrade with outside heat transfer coefficient 8.5 watt per meter square degree centigrade. The surface temperature of the cable is likely to be 65 degrees centigrade due to the heat generation within. Will the rubber insulation, the thermal conductivity K is 0.155 watt per meter degree centigrade be effective? Is yes, then how much? Let's start the solution with the figure. Here is the figure. Inside the figure there is a solid cylinder and the outside is a insulation having a thermal conductivity K, which is given in the data. HO is the convective transfer coefficient. R2 minus R1, that is the thickness of insulation. So as per the given data, here the R1 is 10 divided by 2, that is 5 mm. T1 is the surface temperature 65 degrees centigrade. Atmospheric temperature or air temperature is given 20 degrees centigrade. Thermal conductivity K, that is 0.155 watt per meter degree centigrade, and HO, that is the convective transfer coefficient, that is 8.5 watt per meter square degree centigrade. So for a cable, means considering like a cylinder, critical radius RC is equal to K by HO. Using this equation and putting the value of K and HO, we get the critical radius is 18.235 mm. Here RC is greater than the radius of the cable. Hence, the rubber insulation up to the thickness of 13.235 mm, 18.235 minus 5 will be effective in heat dissipation. The maximum heat dissipation per meter length of the cable will be Q maximum, or a heat transfer per unit length, Q by L, that is equal to 2 pi into T1 minus Tr divided by ln Rc by K1 divided by K plus 1 upon HO into Rc. Putting the value in this equation, then we get 19.1 watt per meter, that is our answer. Take one another example, and here is the given data. A wire of 6.5 mm diameter at a temperature of 60 degrees centigrade is to be insulated by a material having thermal conductivity K is equal to 0.174 watt per meter degree centigrade. Convection heat transfer coefficient HO is equal to 8.722 watt per meter square degree centigrade. The ambient temperature is 20 degrees centigrade. For the maximum heat loss, what is the minimum thickness of insulation and heat loss per meter length? Also find the percentage increase in the heat dissipation too. Let's start with the given data. Here the R1, that is 6.5 divided by 2, so that is 3.25 mm, is equal to, convert into the meter, 0.00325 meter. Conductivity is 0.174 watt per meter degree centigrade, and the convective heat transfer coefficient HO, that is 8.722 watt per meter square degree centigrade. For maximum heat loss, the minimum insulation thickness corresponds to critical radius of insulation, which is given by the equation Rc is equal to K by HO. Consider here the cylinder, and putting the value of K and HO, we get the critical radius, that is 19.95 mm. So that minimum insulation thickness, that is Rc minus R1, is equal to 19.95 minus 3.25, that is equal to 16.7 mm. That is our first answer. Now let us calculate the heat loss per meter length. So we can solve this answer by two cases. Case number 1 without insulation, and case number 2 with insulation when critical radius is or critical thickness is used. So solve the case 1 without insulation. So say Q1, that is equal to 2 pi L inside the bracket temperature difference T1 minus Tr divided by 1 upon HO into R1. Putting the value in this equation, we get the Q1 is equal to 7.124 watt per meter. Take case 2 with insulation when critical thickness is used. So that equation, say Q2, that is equal to 2 pi L inside the bracket temperature difference T1 minus Tr divided by the RTH total. So that is ln into Rc by R1 divided by K plus 1 upon HO into Rc. Putting the value in this equation, we get 15.537 watt per meter. So percentage increase in heat dissipation, that is Q2 minus Q1 divided by Q1 into 100. So Q2, that is 15.537 minus Q1, that is 7.124 divided by 7.124 into 100. So we get 118.09 percentage. Now let's learn our next topic, that is heat transfer through extended surfaces, fins. The rate of heat transfer from a surface at a temperature Ts to the surrounding medium at T infinitive is given by the Newton's law of cooling at Q convection is equal to HAS into temperature difference Ts minus T infinitive, where the AS is the heat transfer surface area and H, that is convective heat transfer coefficient when the temperature is Ts and T infinitive are fixed as per the design. There are two ways to increase the rate of heat transfer: to increase the convective heat transfer coefficient or to increase the surface area AS. Now increasing the H may require the installation of a pump or a fan, means the forced convection, but this way may not be practically possible. So whenever available surface is found in insufficient to transfer the required quantity of heat with the available temperature drop, and convective heat transfer coefficient extended surfaces or fins are used. Fins made of highly conductive materials like aluminum. It is necessary to use the in heat transfer between a surface and gas, as the convective heat transfer coefficient is rather low in this situation. Fin surfaces are manufactured by extruding, welding, wrapping a thin metal sheet on a surface. In many engineering applications, large quantities of heat have to be dissipated from small areas. The fins increasing the effective area of surface with increasing the heat transfer by convection. The fins are manufactured in different geometries depending upon the practical applications like economizer from steam power plant, convectors for steam and hot water heating systems, radiators of automobiles, air cooled engine cylinder heads, cooling coils and condenser coils in refrigerators and air conditioners, small capacity compressors, electric motor bodies, transformers and electric equipments. In practice, all kinds of shapes and size of fins are used. Some of the common types of fins shapes are shown here. So many variety of innovative fins designs available in the market. Number 1, longitudinal fins, annular fins, pin fins, straight fins of uniform cross section and straight fins of non-uniform cross section. The ribs attached along the length of a tube are known as longitudinal fins. The concentric annular disc around a tube are known as circular or annular fins. Pin fins or spines are rods protecting from a surface. For the proper design of fins, the knowledge of the temperature distribution along the fins is necessary. In this topic, the mathematical analysis for finding out the temperature distribution and heat flow from the different types of fin will discuss. The following assumptions are made for the analysis of heat flow through the fin. Number 1, steady state one dimensional heat conduction. Number 2, no heat generation within the fin. Number 3, uniform heat transfer coefficient over the entire surface of the fin, homogeneous and isentropic fin material. Number 5, negligible contact thermal resistance, and number 6, negligible radiation. Consider a rectangular fin extended from a wall surface as shown in figure. Let L is equal to length of fin, B is equal to width of fin, Y that is the thickness of fin, P that is equal to perimeter of fin is equal to 2 into B plus Y, A CS that is the area of cross section that is equal to B into Y, TO that is the temperature at the base of fin at here, and TA that is the air temperature, and K is equal to thermal conductivity, H is the convective heat transfer coefficient. In order to determine the governing differential equation for the fins, consider the heat flow to and from an element dx thick at the distance x from the base. Heat conducted into the element at plane x, Qx is equal to, from the Fourier's law, minus k a into dt by dx at x, that is equation number 1, and heat conducted out of the element at plane x plus ds, that is equal to Qx plus dx is equal to minus ka into dt by dx x plus dx, say equation number 2, and 3, heat convected out of the element Q convection, that is from Ha delta T Newton's cooling law. Here A that is P into dx, P is the perimeter, dx is the thickness, and temperature difference T minus Ta, say equation number 3. Applying an energy balance on the element, so rate of heat conduction into the element at x is equal to rate of heat conduction from the element at x plus dx, or say delta x, plus rate of heat convection from the element. So from the energy balance, say Qx is equal to Qx plus dx plus Q convection. So we say that Qx plus dx minus Qx plus Q convection is equal to 0. Putting the value of Q convection, and that is H into P dx into bracket T minus Ta. Substituting and dividing by dx, and we obtain Qx plus dx minus Qx divided by dx plus H into P, that is perimeter, into T minus Ta is equal to 0. Taking the limit as dx tends to 0 gives that Q dqx divided by dx plus hp into T minus Ta is equal to 0. From equation number 1, putting the value of Qx, and we get K into A inside the bracket d square T by dx square minus hp into T minus Ta is equal to 0. This equation is the differential equation, or you can say that differential equation governing the heat transfer in fins. Dividing both sides by Kas, we get d square T by dx square minus hp by Ka into T minus Ta, that is equal to 0. In general, the cross section area ACS and the perimeter P of fin vary with x, which makes the differential equation difficult to solve. In the special case of constant cross section and the constant thermal conductivity, the differential equation above reduces to d square theta by dx square minus m square theta is equal to 0, where m is equal to under root of hp by k into ACS. Here theta is equal to T minus Ta is the temperature excess. Equation represent a general form of the energy equation for one-dimensional heat dissipation from the extended surfaces or fin. The general solution of this linear and homogeneous second-order differential equation is of the form theta is equal to C1 e raised to mx plus C2 e raised to mx. Here we know that theta is equal to T minus Ta, so we can also write T minus Ta, that is equal to C1 e raised to mx plus C2 e raised to minus mx. Where C1 and C2 are the constants, these are to be determined by using proper boundary conditions. One boundary condition is theta is equal to theta 0, that means T0 minus Ta at x is equal to 0. The other boundary conditions depends on the physical situation. The following cases may be considered to solve the value of C1 and C2 with the help of other boundary condition. Case number 1, the fin is infinitely long and the temperature at the end of fin is essentially that of the surrounding fluid. Case number 2, the end of fin is insulated, and case number 3, the fin is of finite length and losses of heat by the convection. So guys, it's the end of part number 3. In the next part we will discuss or we derive the heat dissipation equation from the rectangular fin for these 3 different cases. So thanks for watching, keep learning, and wish you good luck to all.